All right. So thanks for attending today. And we want to thank each of you that attends. There's I put some stuff in the chat box. If you want a certificate of attendance for today, you can follow this link and register for a certificate of attendance. There's a Q&A box up here. So if you want to ask any questions, even as you're going along, if you have a question, you can ask, you can put it in the Q&A box and we'll answer it. As we're going towards the end. So there's a place here for certificate. I'll mention it again. There's a place here for certificate of attendance. And then there's a Q&A box where you can, if you have a question as we're going along, just go ahead and answer. Just go ahead and ask it. Don't wait, and then we'll have a Q&A session at the end. So I went through and I made the presentation, and most of the presentation today is going to be on distillation. And I did cover heat exchangers and pumps a small amount. I'll probably come back in November and do another one where I do a small amount of distillation and talk about heat exchangers and pumps more. So today is more, we're covering distillation more today. I'll cover heat exchangers and pumps briefly. I may come back in November and talk about distillation a small amount, and then talk more about heat exchangers and pumps. Okay. So what's our agenda today? I believe every presentation should start with some safety. We're going to talk a little bit about sustainability. Most of what we're going to talk about today is distillation design. I've got a small amount of heat exchangers and a small amount of pump design, and then we'll have a Q&A. And so we want to cover each of these topics, and then I may come back in November and talk more about heat exchangers and pumps. Okay. KLM Technology Group, based in the US since 1995. It's a technical consultancy group providing specialized services and equipment to improve process plant operational efficiency, profitability, and safety. Our core business is training, like today. We do webinars, we do online training. During COVID, we did a lot of online training. Typically, I show up and do in-house training. We're planning a large training in Malaysia in February. We do engineering documentation, engineering consulting. Part of our engineering documentation, we do engineering design guidelines. We also publish a bi-monthly magazine. We do engineering consulting, we do PSM consulting, and we provide specialty process equipment, distillation, heat exchangers, and pumps. What we're talking about today is some of the specialty equipment that we help provide. Today, we're discussing introduction of process equipment. We also offer other training courses: advanced distillation, heat exchanger design, refinery crude unit design, ethylene unit design, natural gas processing design, as well as other process unit and equipment groups. They can be found on the website, klmtechgroup.com. So what's our agenda today? Safety, sustainability, distillation, heat exchangers, pumps, Q&A. Each one of these topics we've covered in our bi-monthly magazine with our great authors. We've been publishing 7 years. I'm very honored that a lot of people, amazing amount of people, read the bi-monthly magazine. We publish it in multiple places, and we have great authors. We'd like, if you're interested in writing an article, send us an abstract, and we'd be happy to help you publish in Engineering Practice Magazine. Safety. First thing on the agenda, safety. HSE is the #1 concern. No project or operation can be classified as sustainable, optimized, or excellent unless it's done safely, healthy, while minimizing environmental impact. We've made great improvements in safety in the last 50 years. And so everybody's really happy. We've really done great in HSE. But we started from such very poor performance. In the 70s, we had multiple deaths and multiple incidents because we've made, and we think we are doing so good in safety. So we've gone from maybe an F, a failing grade, to an average C grade. We've done well, but there's still great opportunities for improvement. So we've come from such a poor place to where we're maybe an average student. The parents are happy, but not really. We shouldn't be happy with C grades. We've done well, but there's still great opportunities for improvement. Let's continue to improve the efforts. HAZOPs, my complaint about HAZOPs is there's typically not enough senior people there. KLM has senior engineers with over 35 years of equipment design, operation has experience, can review your operation, improve your health, safety, and environmental performance. So we've gone from an F to a C, but I still think there's work to do on safety. Sustainability, process equipment troubleshooting. So let's talk a little bit about sustainability. That wasn't nearly enough about safety. Sustainability is a societal goal that broadly aims for humans to safely coexist on planet Earth over a long period of time. The quality of causing little or more environmental damage and therefore able to continue for a long period of time. So these are definitions, some definitions of sustainability. So what are some sustainability buzzwords? Green energy, which is wind, solar, and hydrogen. Electric cars. Blue energy, which is obtaining energy from the sea. Renewable energy, renewable kerosene and diesel, biodiesel, recycling, and conservation. What should be the real ranking of these ideas or programs? Well, I can tell you my opinion. How should these be ranked? So let's go back to the definition one more time. Sustainability is a societal goal that broadly aims for humans to safely coexist on Earth over a long period of time. So in my view, sustainability, safety has to be number one, and I said it in the safety section. Number two has to be conservation. The bottom line is use less energy. And as engineers, that's our job, to design plants, to reduce energy, use less energy, use less feedstock. Okay. If we use less energy and less feedstock, I don't need as much green energy or blue energy. So to me, this number one is safety. Number two is have to be use less energy. All through this presentation, I'm going to talk about distillation, pumps, and heat exchangers and how to use less energy on each one of them. Recycling, very important. Then green energy, wind, solar, and hydrogen. Blue energy from the sea. All right. Renewable diesel and kerosene and biodiesel. And I put cars last because it's got some question marks beside it. Every real engineering study that I've seen says we don't know the impacts yet on electric cars. Okay. You've got, we're mining for the battery components. We've got the battery recycles. We've still got to produce the electricity. So there's a whole big question mark. How sustainable is electric cars? But currently, green energy and electric cars tend to be the two hot things that we're talking about. Number one has to be safety. Number two has to be, let's just use less energy. Recycling, green energy. Conservation is important. Part of any process plant optimization. The two largest drivers are feedstock and energy. And exceedingly small feedstock to high value products can lead to exceptionally large profit improvement and sustainability. If I use less feedstock and I produce high value products, that's important. For most plants, you should have a feedstock reduction team. All right. Many times only a few bad actors are leading to the loss of feedstock to high value products. Energy should be tracked weekly and monthly. Total energy should be tracked, energy per ton of high value products. The industry standard, every time I say this, people are surprised. The industry standard for major companies says energy is reduced 1 to 3% per year. What is your plant's current performance? The major companies are reducing energy 1 to 3% per year. When I go to most plants, they have the same energy performance or they're getting worse. The best performing plants see yearly increases of greater than 3%. And how do they do that? Well, I'm going to talk to you today in how they do that. Okay. So part of this presentation is how do you improve your energy, which is the main part of conservation and sustainability. Energy is a function of energy. Conservation is a function of several items. Equipment design. I can design distillation equipment that is 10% more efficient. Okay, typically we buy vanilla type equipment. Okay, we don't buy typically we don't buy the best efficient equipment because of cost, but they don't realize it's a small amount of cost difference. You make a huge amount in equipment. You make a huge amount in energy savings, plant reliability, motor power factors. I was consulting for a EV styrene plant. So one of the things when I go consult, I go back and I track their energy for several years. So I'm at this EV styrene plant and the energy trended up over the last 5 years. And they had just bought low energy catalyst. And I'm going, guys, something's wrong with this picture. You bought low energy catalyst and your energy's tracking up. So I'm in the meeting and I'm asking, we're in Asia and Asians don't say much in the meeting. So nobody said a word in the meeting. So after the meeting, the electrical engineer comes to me and he said, well, why energy's tracking up is we're buying very low cost motors, which have very poor power factors. So they were buying motors with low efficiency. So a good motor might be 80 or 85% efficient. A low cost motor might be 70% efficient. There's 10% efficiency. A large motor, you're buying 10% efficiency. If you're in a hot climate, that efficiency is lost in heat. So the motor's not going to last very long and it uses less energy. Pump efficiencies. We're going to talk in this presentation today a little bit about pumps, but pumps efficiencies, current pumps with CFD modeling can be greater than 90% efficient. Again, that's lost work goes to heat. Most pumps in an older plant is probably 80% efficiency. So if I do, when I buy a new motor, if I buy a better power factor, when I buy a new pump, if I buy better pump efficiencies, that's how the majors are driving it down 3% a year. If I replace trays, I need to replace them with higher efficiency trays. Lighting, everywhere I walk, I can see old style lighting, but we know LED is significantly more effective. Equipment installation. So you can take a Polaroid camera, you can take special film, and you can walk around and take pictures of your plant and see where you're losing heat in your insulation. Heat exchangers. I'm going to talk today about how poorly heat exchangers typically are designed and things you can do to improve that. Distillation. We're going to talk about distillation. Heaters and boilers. Every heater I walk up to almost has too much excess air. Okay, so the first thing we need to do is look at energy. Okay, the best way to be sustainable is to use less energy. If your energy cost is increasing, you need to put the energy reduction team. Just forming the team normally sees an energy reduction. It's amazing what increased focus can accomplish. You need to review equipment design, particularly your heat exchangers, heaters and boilers, and distillation equipment to help reduce energy, often by just adjusting operating parameters. Each time you replace a piece of equipment, you should improve the energy piece of that equipment. Don't just replace in kind. Go ahead, buy a better pump, buy a better motor. Every time you open your distillation column to inspect them, buy better trays. A 1 meter tray costs $1,500. Okay, it's not crazy money. This is how the industry gains 1 to 3% yearly by upgrading the equipment. You should not replace in kind. You should replace with a higher piece of equipment. We want to be sustainable. It also saves you money. Okay, so it's a double win. I make more money and I'm sustainable. Your team should be taught to specify replacement equipment for increased energy efficiency, often with only a small cost. There's going to be a small cost increase. That's why they didn't do it from day one. But it has a huge return on investment, particularly when the price of natural gas is kind of high like it is now. So there's sometimes can be months 3 to 4 months return on investment. Pumps, motors, heat exchangers, distillation equipment are all items can replace with higher efficiency equipment. So for years, we've lost the battle on this delta. Okay, for 3% more, I can buy a high efficiency piece of equipment. Okay. Back when natural gas was cheap, it didn't make sense. Today, when the price of natural gas is very high, when we're trying to conserve, we're trying to be sustainable, that 3% now has a very large return on investment. KLM's senior team can assist you in specifying replacement equipment for increased energy efficiency, often with only a small cost increase, which is a large return on investment. So one thing you might want to do is have somebody look at your specifications when you're going out for bids. You need to specify a certain power factor for a motor. You need to specify a certain efficiency for a pump. You need to specify in distillation, you need to specify a certain efficiency and a certain fouling resistance. These are things you should have in your specifications when you go out for bid. It's going to cost you a little more money, but it's going to pay back very quickly. So we've talked about safety. We've talked about sustainability. Let's jump into distillation a little bit. Okay. Distillation troubleshoots. Do the simple checks first. Look at temperature and pressure compositions. Let's talk about troubleshooting tools, and then let's talk about some tower inspections. But so you're going to call me to come do a troubleshooting. You got a problem tower. So first thing I'm going to do is do the simple checks first. Then I'm going to look at temperature, pressure compositions. I'm going to run a simulation. We're going to look at some troubleshooting tools, and then we might have to actually open up and inspect the tower. So these are some distillation troubleshooting tools. But do the simple checks first. As engineers, we want to do a simulation first, when many of the issues with distillation is instrumentation related. All right. So the first thing we want to do is we want to verify the tower levels. We work with the operators. We confirm the level. So we go up on the overhead receiver. There's a sight glass right here. We can either open the overhead storage control valve, or we can open the reflux, and this level should track down. We can go to this sight glass here. We can have them open the bottoms to storage. This level should track down. What percent of the time would you guess that when you go to a tower troubleshooting, they cannot find the tower levels? Okay, so I show up. The first thing I'm going to go do is go look at these two levels. What percent of the time would you guess they don't know where the levels are? Now, everybody think levels are easy. Levels are not easy, and they're not very accurate. Okay, we're going to talk about that. In my career, 20% of the time when I show up and the tower's not working, it's always the tower bottoms level. If the tower bottoms level is higher than the reboiler will not function. And what I normally do, I'll put a pressure gauge on the tower bottoms line and calculate the tower bottoms level. You can take row GH, and I can tell you how high up in the column. Usually it's above the sight glass, and they don't really know where the level is. So I can put a pressure gauge on the tower bottoms line, and I can calculate the tower bottoms. So we calculate the tower bottoms level, how high it is. We start lowering it down. When we get it below the reboiler return, the tower sometimes will start working. So the challenge is the tower bottoms may be frothy and at a higher temperature than the level leg because of Bernoulli's equation. All right. So if you go to a hot system, the sight glass, what's in the column is always higher than what's in the sight glass. Can be 10 to 15%. I've seen it even be 20% higher. Okay. So levels seem easy, but they're really not. Okay. If you've ever seen a movie of what the inside of a distillation column looks like, or what the inside of a tower looks like, it's frothy, and that level in the column is going to be much higher than the level in the sight glass. Next thing I want to do is perform a tower pressure drop. So if the Levels are okay. Let's perform a tower pressure drop. So there's normally 3 places I can put a pressure gauge. I can put one at the top of the bottoms level right here. I can put a pressure gauge right here. I can put one on the overhead line. Typically, I can put a pressure gauge right here, and I can typically put a pressure gauge right here. Okay, so I can put a pressure gauge in 3 places on this column. So this measures the pressure drop across the column. These 2 measure the pressure drop across the overhead condenser. Okay, you should use the same gauge, and one person should read the gauge. Everybody reads gauges different. All right, so you should use the same gauge, and one person should read the gauge. Typically, I go read the gauge. Okay, if I drop the gauge, you start over. Okay, you get a brand new gauge, you go to the instrument shop, you get it calibrated, you carefully install it in the 3 paces, and the same person reads the gauge. In advance, you can review the design data and know approximately what the pressure drop should be. Okay, all right. Suppose you have 30 trays and you're expecting about a 3-pound pressure drop, 0.2 bar. What does it mean if you have a high pressure drop across this column? Well, it could be fouling, could be flooding. Your tray might have dropped down on another tray. What does it mean if you have very low pressure drop? Well, all the trays could be laying in the bottom of the column. Okay. What is the normal design pressure drop of a heat exchanger? Should be about 5 pounds, 0.35 bar. What does it mean if you have very high pressure drop across this heat exchanger? Well, that could be fouling. Okay. What does it mean if you have very low pressure drop across this heat exchanger? Well, what that normally means is you really don't have very much reflux, and this reflux meter may not be telling you the truth. Okay. So so this pressure drop can tell you a lot. It can tell you if the trays are in place. It can tell you if the heat exchanger is fouled. It can tell you if maybe I don't have enough reflux. So perform a tower pressure drop. Again, in my career, about 20% of the time, you can identify the problem with the tower pressure profile. Once you've identified there's a problem with the columns, you can now scan the column to get a better picture of what's happened inside of it. So run a pressure drop. If it's much higher than design or much lower than design, go get a column scan. Next thing I want to do is perform a tower temperature profile. You can take a temperature gun and survey the tower temperatures. Okay. So I can look at the feed, the bottoms, the overhead temperature, the reflux temperature. So I can survey all of these temperatures, right? So I can look at the feed, I can look at the overhead, I can look at the cooling water in and out, I can look at the bottoms, I can look at all of these temperatures, all right? What happens if your feed is much hotter than design? What can happen if your feed is much colder than design? Most time, if I'm going to design a column, I want to heat this feed to where 50% goes up and 50% goes down. So I want it to be about 50% flashed. All right. So if it's much hotter than design, I can flash a large part and I can flood this part of the column. If it's much colder than design, I make too much liquid and can flood this part of the column. So it's important that your feed be roughly what the designer designed it for. If he designed it for low temperature, well, he probably made these trays a little larger, or he should have made these trays a little larger. What happens if your reflux is much hotter than design? So if my reflux come in and it's hot, what I really want it to do is come in at a certain temperature, cool this vapor that's coming up and go down the column. If it's hot, it's going to come in and it's just going to make a recycle through this overhead condenser and even make it hotter. What happens if your reflux is much colder than design? Well, if it's too cold, I can actually flood the top of the column here. Okay. What does it mean if you're cooling water in and out of the same temperature? So this cooling water and this cooling water out, the same temperature, can mean two things. Number one, this heat exchanger is fouled. Number two, it can mean, again, you have no reflux. Okay. So we had a, I worked in a Houston refinery 16 years, and we had a debutanizer column on the FCC, which took the C4s out of the gasoline. So it was a very important column. And we did a turnaround, and coming out of the turnaround, the column no longer worked. All right. So they did a whole bunch of troubleshooting. They brought in a whole group of people, and it was decided, well, maybe they need to retray the column. So they shut the FCC down. They retrade this column because they weren't making on spec gasoline, which is kind of important, and started to back up with the new trays. It still was not on test. So I get interested in distillation. So my boss asked me to go down and look at this column. So I went down and looked at it. And so young engineer was walking around, and he noticed that this and this was the same temperature. Okay. And he also noted this control valve was not open very much. So the combination of this temperature not seeing any and this control valve not being open, he had him open this control valve. 100% of flow is 70% of a control valve. He had him open this control valve. Tower started working. They shut down the FCC, retrade this column, and this flow meter wasn't working. Okay, so it's very important that you do some troubleshooting. Do the simple checks first. Perform, verify the levels, perform a pressure survey, perform a temperature survey. Okay. So in the chat box, I've got two things. If you want a certificate of attendance, you can follow this link, and there's a Q&A box up there. If you want to ask some questions, we can look at the Q&A box, and I've got two questions. Tire bottoms has a baffle and a hole. What is it used for? Could you share this PDF to us? Okay, so tire bottoms has a baffle and a hole in it. Typically coming out of the tire bottoms, I really want to go through the reboiler at least once. Okay, so the tray should drop into one side of the baffle, go through the reboiler, and come back at the bottom on the other side. So the reboiler actually is really your last tray. So I really want, as much as possible, for the liquid to go through the reboiler at least once. So the bottom of the tire has a baffle, and it's also got a small hole in it. So if you're draining the column, you don't want to leave that level of hydrocarbons on the other side of the baffle. So typically I want a hole in the bottom. So when I drain the column out, all the liquid will come out of the side of the baffle. Can you share this PDF to us? I'm going to share the whole video on YouTube when we finish. There's Carl Comet CPE has a certified practicing engineer has a YouTube channel, and I'm going to share this whole video. What is the function of the vortex breakers at the bottom of the outlet? If you're not close to the equator and you pull liquid anywhere else in the world, the liquid will form a circle, all right? And you'll actually pull air into the pump. So the function of the vortex breakers at the bottom outlet is to stop this circulation, okay? And to not have air, because the pump's not designed do gas? Can you share the most difficult process? Research my solution your team did. Okay, so we'll end. I've got several things we can talk about, and then I'll do that. I'll do that later. Okay. Anyway, so there's two things. If you want a certificate of attendance, you can do this, and you can if you have a question, you can go to you can put them in the Q&A. All right. So that's kind of and we'll go back and answer some more. All right, troubleshooting. So I've done the simple parts. I've looked at the feeds, I've looked at the levels, I've looked at the temperatures, I've looked at some of the floats. Then you go sample the feeds. Has the feed changed from the design? Build a mass balance. If it's not within 2 to 5%, get your meters calibrated. All right. Typical normal orifice plate is only 2% of accuracy. The current micro motions are much better, but a normal orifice plate, it's only 2%. So try to build your mass balance to within 2 to 5%. Then you go performance simulation. Has the temperature and pressure profiles changed? Go look at hydraulic profiles. I talked to you that we'd probably come back later and do a second part to this. At part 2, I'll come back and I'll talk about hydraulics. In part 2, I'll talk about hydraulics. I may do that in November. Do the sample checks first, sample the feeds, build a mass balance, perform a simulation. So these are troubleshooting tools. So KLM is recognized as leader in distillation equipment, design, operation, commissioning, and troubleshooting. Typically, a company will have a design guy, they'll have some guy that troubleshoots it, and some guy that commissions it. Okay, so they'll typically have 3 different people. I've been very fortunate. I've got to do design, I've got to do operation and troubleshooting. And so I will show up, and I'm going to bring my 40 years experience to you. And so typically a company might have to send 3 people to do a troubleshooting, where I'm probably going to bring that much experience with me. Okay, we can provide process studies, we can do engineer operations trainings. Really, each one of these subjects should be 3 to 4 day class. You know, distillation, heat exchangers, and pumps. Each one of them should be a 3 or 4 day class. Tower inspections. I've probably climbed through 100 towers in my career. Okay. Distillation replacement equipment. Okay. So we don't replace in kind. If you're going to replace equipment, always replace with more efficient. Commissioning assistance. Me and my team, I've got a really good team in Malaysia. We will come and help you commission some units. What are the major equipment issues? Well, in my career, incorrect installation has been huge. All right. If I don't install it correctly, it's not going to work. All right. The challenge is that very few people really know how they're supposed to be installed. And I've actually went behind the majors and corrected some of their mistakes. Even the major companies, major distillation companies, have installed them wrong. Operation. What are equipment mistakes that we do in operation? We over reflux. All right. So I walk into most units, they're using too much reflux. Well, if I using too much reflux, I'm using too much energy in the reboiler. All right. And then high pressures. If I walk into most units, you can lower the pressure on most columns. If I lower the pressure, the relative volatilities get better, and you end up having less energy and better recoveries. And the third major issue is we buy low efficiency equipment. Okay. A 1 meter tray costs about $1,500. Okay. What costs the money in the distillation is the foundation, the tower, the overhead lines, the overhead condensers, the pumps. That's the electrical, the instrumentation. That's what's expensive. What does the work is the tray. Okay. And we want to save money on the tray. Don't save money on the tray. Go save money on all the other pieces. Tower inspections. A large problem in many is the incorrect installation, leading to loss of product quality, higher energy, and run length plant reliability. So basically, if I don't install it correctly, okay, I'm going to have loss of product quality. I'm going to have higher energy and shorter run lengths, which can be $1 million effect in a large plant. Not installing it correctly can be $1 million. Many companies do not have the expertise to review tower inspections. If it's a large unit, I'm going to show up. I'm going to bring one of my senior guys from Malaysia with me to show up and assist your tower performance. What are things we're going to look at? We're going to look at the downcomer clearance, the free area, top width, bottom width, all of these things. I got a whole series of pictures where I followed behind one of the major companies and had to go correct their mistakes. And here's some mistakes. All right. So this reflux pipe should come in behind this false downcomer and flow evenly across the tray. Well, because it's not installed correctly, it's going to wipe out the efficiency of this tray and the efficiency of the tray below it. Well, if I got 30 trays, I've wiped out the efficiency of 2 trays. So that's 6% of the efficiency of this tower is gone. So you got to use 6% more energy just because you didn't put this reflux nozzle behind this tray. This is my hand. I took this picture and I'm measuring the downcomer clearance. That's just something you just got to do. Distillation replacement equipment, trays, random packing, structure packing, demister pads. All right. KLM provides distillation replacement equipment at significantly lower cost than the major distillation companies due to our lower overhead costs. Most major distillation companies have thousands of employees in worldwide offices, leading to a high fixed overhead cost. KLM has limited overhead costs, and we pass the cost savings on to your team. We provide the same specification, trays, random packing, structure packing, and demister pads, as well as a senior engineer, typically me, to review the selection. If your current system has short run lengths, should we consider a more reliable replacement? Maybe a more fouling resistant or a stronger design. Okay, and these are typical crude unit trays. And they should probably be a little more fouling. These are not fouling resistant designs, and they're also not probably strong enough. Stronger and more fouling resistant designs are very important for random packing and demister pads that have high fouling failure rates. All right, so let's talk about this for a second. Here's an ethylene plant case study. A plant in Malaysia opened their quench oil tower and found the random packing had disintegrated, causing very high pressure drop and fouling. Why did this happen? So they had obviously had some rings. That picture shows all the rings disintegrated, and the fouling, because it's now, once the rings disintegrated, it acted like a filter for the coke fines from the ethylene furnace. All right. Of course, you had a really high pressure drop. You had to shut the column down. This is a $1 million problem for a large ethylene plant. One cause might be galvanic corrosion. The packing was stainless steel and the tower was carbon steel. Always consider galvanic corrosion when you're designing with multiple metallurgies. All right. So if I've got a quench oil tower, a quench water tower, you probably don't want to put stainless steel packing and a carbon steel wall. All right. If you do, this is what's going to happen. The licensors, the very first time you buy the column, typically will put carbon steel packing in. So the licensors will, and then the vendors will come back behind them and sell you stainless steel. Okay. So, but typically the ethylene vendor, the very first batch of packing you get will be, you'll have a carbon steel wall, you'll have a carbon steel packing. When you replace it, the vendor's going to try to sell you stainless steel. Unless you understand galvanic corrosion, it's not going to last very long. Opportunity loss was well over $1 million for this ethylene plant. You had high energy losses and short run lengths. Okay. So you need to think about galvanic corrosion whenever you're doing mixed metallurgies. You have water, you have low pH or high pH, you're going to have galvanic corrosion. Gas processing case study. This is a picture of fouling in an A-beam column. This tire was packed with Paul rings. Paul rings have low efficiency and are not fouling resistant. Why would you pick a low efficiency ring with high surface area in a fouling system? Okay, so this was a poor choice of random packing. The opportunity loss is not as large as an ethylene plant, but why would you choose a low efficiency and a not fouling resistant packing? So typically this is IMTP, IMTPE type packing. It is been tested independently and it has much higher efficiency. All right. Might even be the same cost, might be a little more cost, but you're going to get much higher efficiency with IMTP. And now amines going to foul no matter what, but you might as well pick a high efficiency packing. Don't pick a low efficiency packing. For demister pads, it's important to understand the failure cases. KLM can provide equipment designed stronger with higher fouling resistance and longer run lengths. We quote a lot of demister pads. And I have a question. Why should a caustic tower, which has a stainless steel shell, no, I'm sorry, which has a carbon steel shell, have a stainless steel demister pad? Most every caustic tower I go to they're going to have a stainless steel demister pad. Probably should be a some kind of polymer. We know stainless steel and caustic are not compatible. It's just going to leave. All right. You're going to get galvanic corrosion extremely bad. You're going to get caustic stress. So again, if I'm going to specify a caustic tower, I'm not going to specify a stainless steel pad, but most caustic towers I walk up to have stainless steel pads. So people aren't understanding this metallurgy, caustic versus galvanic corrosion, caustic attack. So make sure. The other thing I would do when I design a demister pad, the bottom 100 millimeters, I'm going to have a little thicker, a little larger openings. The top of the demister pads, I'm going to have very small openings. The bottom of the demister pad, I'm going to have a little bigger mesh, so it'll last longer, and that doesn't cost a lot of money. So don't put stainless steel in a caustic tower. And then if you are going to buy a demister pad, put the bottom, I don't know, 4 inches, what is that, 200 millimeters, bigger mesh in the top mesh thinner. And KLM, we quote a lot of demister pads. We've got really good team to do demister pads, and we're going to try not to make the metallurgy mistakes, and then we're going to try to make it more efficient and last longer. Okay, so I got some more questions. Let's see. Recording also. I'm in the office. I'm not able to listen properly. Okay, what we'll do, we're going to put this up on YouTube when we finish. Ask the question, we'll install an flint baffle on rebolder return is applicable. The image plates reduce erosion caused on the side of the shell. Yes, I would. I like impingement plates on the rebolder return, particularly if you're causing erosion on the side of the shell. I've got a paper on what that baffle should look like. I've got some CFD models And I have a paper, I think I've published it in the magazine, but I have a paper on what that baffle should look like through CFD models. So send me an email, and then I'll show you, I'll send you a copy of what that baffle should look like. Faster, one reboiler chassis, one reboiler standby isolated valve closed without PSV. If asked him, said it doesn't have PSV because the reboiler is designed for high pressure equal to. Is this normal? This is not normal, and 3 people died at Williams ethylene plant in Louisiana. All right, so this is not good, and you've had multiple deaths from having a reboiler blocked in. Okay, so I would strongly have a mini heads-up for this. Then I would look at this case study from Williams. I would look at this case study where 2 or 3 people died because the boiler blew up. Have you ever exploded a desalter trip due to high amp breathing because of high conductivity of crude? We see in our plant, crude, high emulsion comes in, just wondering. Typically, that's normal. You have to control your pH so you can look at you can keep the conduct, you can keep your emulsions down. Okay, so you've got to make sure you control your pH. I have a whole 1 hour presentation on desalters, and I've thought about doing a webinar on desalters. Certificate of attendance. What you do to avoid galvanic corrosion in the columns is you use the same metallurgy. All right, so if I have a stainless steel column, I can use stainless steel packing. If I have a carbon steel column, I have to use carbon steel packing. Now, the vendor don't want to sell you carbon steel packing because it's a pain for him, but he can do it. If he won't do it, KLM will provide you carbon steel packing. All right, but you have to match the metallurgy. It's not as important if you don't have water, if you don't have polar issues, because you need that ionics to do the galvanic corrosions. Have you any recommendations for software programs for complex mass balance or highly integrated petrochemical plants? Now, what I've done in multiple places, and most major refineries do this, they go build their own internally. All right. So you can hire a third party to do it for you, but the third party is going to cost you $1 million, and they typically don't work well. What I've done, I've taken a group of young engineers in 3 different ethylene plants, and we built our own little complex mass balance systems. Comparing stainless steel packing, carbon steel wall, and carbon steel packing, which combination would last longer? Obviously, if you don't have stainless, if you don't have ionic components, all right, if you don't have water, if you don't have low pH or high pH, you can use stainless steel and carbon steel. If you have ionic components, if you have caustic, if you have water, you probably don't want to put mixed metals together. Okay, that's just the way it goes. Okay, so let me ask you another question. This remind me of a question. Which do you want to be the sacrificial anode? Do you want the wall to be the weak link, or do you want the tray to be the weak link? Trays are only $1,500 per 3 meters. The wall is crazy expensive. I want the tray to be the weak link, and I want to replace the trays. I go to a lot of refineries, and the top half of the crude tower they've had to replace. That's very, very expensive. They would have been better off to replace the trays. Okay, so good questions. Good questions. All right, keep going. Okay, distillation requirement. If your current system has acceptable run lengths, lower fouling potentials, you should consider high efficiency device to improve energy. If you replace your trays, your heat exchangers, your pump in kind, you will not be regaining the 1 to 3% energy reductions, increased plant reliability and product quality. For distillation, we can give you 10% more efficiency. So you use 10% less energy. We can also give you better, product purities. And trays are not expensive. Trays are about $1,500 for a 1 meter tray. Compared to a conventional sieve deck, which most of you have, a high efficiency tray can see greater than 5 to 10% efficiency gains, as well as 20% capacity gains. Distillation can be as much as 50% of a plant's total energy, particularly in a refinery. All right. So if I can take and gain 10% just replacing the trays, I can reduce the plant energy 5%. And it's not expensive. A 1 meter tray costs about $1,500. So this is a tremendous return on investment. If you replace in kind without a review of the best replacement, you'll not be gaining any reductions, increasing plant reliability, product quality, and you won't be sustainable. Okay, so you need whenever you replace a piece of equipment, do not replace in kind. All right, so we've talked about safety, we've talked about sustainability, we've talked a little bit about distillation. I've not covered heat exchangers or pumps very much here. I'm going to go through them quickly. But you're looking at we'll talk a little bit about heat exchangers, a little bit about pumps, and then we've got a few more Q&A questions. I've kind of been answering the Q&As as you go along. If you want a certificate of attendance, we put a link in the chat box here for a certificate of attendance. There's a Q&A box, which we're still getting questions on. And there's two things there's a couple of things you might want to consider doing. We have a YouTube channel called Carl Comet's CPE, Carl Comet Certified Practicing Engineer, that will post this video live. We'll post this video, and I got to go edit it first. And then we'll post this video. We also have Engineering Practice Magazine, where we talk about each one of these things. We do training. We'd be happy to come help your team. We'd be happy to come. If you don't want to buy equipment from us, the minimum you should do is let us review the data sheets. Don't buy replacement in kind. Upgrade as you're going. Okay, heat exchangers. All right. Typical heat exchangers designed with very basic limited optimization. And they're typically designed wrong. And I'm fixing to show you how they're designed wrong. If you're going to replace a heat exchanger, you should not replace in kind. If you have a fouling service, your heat exchanger should be designed to be fouling resistant and improve heat exchange as well as reliability. Almost every fouling service heat exchanger that I've seen is not designed very well, and I'm fixing to explain to you why. So here's some pictures of some typical heat exchangers. All right. So in this particular heat exchanger, the baffle goes all the way down to the bottom. And I've got this dead zone of fouling material right here. This heat exchanger has a dead zone of fouling material of at least 15%, right? You can see it. All right. If you have a fouling service, do not take your baffle all the way to the bottom. Simple. Okay. You have a small amount of flow through this bottom. Now, it'll be slightly less efficient at the start of the run, okay, by having this flow go this way. But by the end of the run, you've lost 15 to 20% efficiency here. Same way with this one. This one, the flow goes this way, right? You can see the baffles all across the top. The flow goes this way and turns this way. Obviously, I've got dead zones right here. All right. So with this fouling setting in this tray, okay, so you notch this top right here. you notch this so that the flow will flow through here, that you won't have these dead zones. Typically, I want to notch this bottom. I still have to support it, but I can put V notches in the bottom of this baffle so that this, I won't lose 15% of this heat exchanger capacity ability. Okay, so if I've got a fouling service, I have to put small V notches in here. All right, so that now I'll lose a little bit of the heat exchange in the start of the run, but my God, I've lost 15% heat exchange here. I've probably lost 15 to 20% of the heat exchange here just by poorly designing these for fouling service. If you got a clean service, if I've got kerosene, put the baffle all the way to the bottom. If I've got any kind of heavy fouling service, don't do this. Okay. Your heat exchanger should be designed to improve heat exchange as well as reliability and reduce fouling. An improved design can increase heat exchange 15% or more. That one heat exchanger was 15 to 20% blocked. All right. Obviously, it's doing no heat exchange. All right. You can replace in kind without a review of your best replacements. You will not be gaining the energy reductions, increased plant reliability, and product quality. Okay. You don't need to look at these pictures very much to see for fouling service, these heat exchangers were not designed correctly. And I can go into your plant, look at your fouling, look at your heat exchanger foulings, and they're not designed correctly. Now we can go in there very simply and put V notches in these, and they'll be more fouling resistant. Okay. So basically, we put baffles in for two reasons. Number one, support the tubes. Number two is to make this flow. All right. But I can tell you, if it's fouling, I'm going to build all kind of solids right here. So I want a small amount of flow through here, right, under this bottom to remove them solids. The start of the run, it's not going to be as efficient, but over the life of the run, it's going to be way more efficient. Okay. So that's kind of what these baffles are for. And so I come here, flow goes under, flow goes over, but the one where the flow goes over, right in here is a dead zone. If you've got high fouling, it's going to build up right here, right here, right here. Okay. And so the obvious answer is you don't design them like this. All right. So it's very important how you design the heat exchanger. That one heat exchanger picture obviously had 15 to 20% less efficiency. All right. Just from not designing properly. These are ugly pictures. That's the only thing I know to say. Under this, I should have some V notches here, obviously. I know these are from an ethylene quench oil system. You know they're going to have fouling. You know they're going to have all kind of tars. You know they're going to have fines, and you don't design traps for them. Okay, so if you're looking at heat exchangers, so typically, how do you design a heat exchanger? Process engineer designs for 120% of flow. Typically, a mechanical engineer can come behind you and add another 20%. So your typical heat exchanger is designed for 140 to 44% of design flow. If you're running at 80% of design, we may be in the laminar flow regime. Okay, because you're running almost half. All right. What happens if I run into laminar flow? Well, we know what happens if you run into laminar flow. My heat duty and my heat transfer coefficient is going to be significantly reduced. All right. So how do you fix this problem? All right. So I know if I'm running significantly lower flow rates, first off, we've way over designed the heat exchanger because they want to put that safety in case they've made an error. All right. And then if we run it low, I run into laminar flow. As soon as I run into laminar flow, I've got 40% loss of heat transfer. All right. As soon as I run into laminar flow. And we know I want turbulent flow. As soon as I run into laminar flow, I've got this extra. I got this extra flow here. I got this extra heat exchange here. All right. So we know this. Everybody knows this. All right. So there's several ways. And I've done this a couple of times. I've come in, I've looked at the flow, I've looked at the area, I've looked at velocity. If it's laminar flow, I've come in, I've reduced 5% of the tubes. All right. Just plug 5% of the tubes. Add some inserts. Some inserts are better than others. There's a particular brand of inserts I don't like. All right. So you need to perform a study. There's a certain brand of inserts that have failed a lot. All right. So that's something you need to know. You need to perform a study. I can't remember the names. I just know what I like and I don't like. You need to perform a study. Determine, are you in laminar turbulent flow? The next turnaround, you may want to reduce some plugs, plug some tubes. You may want to cut some baffles. The next time you buy a heat exchanger, don't just buy a replacement in kind. Go look at what you're doing. If you have pictures that look like these pictures, you're not doing a good job on heat exchanger design. KLM has a senior team. The last 5 years, we probably designed 30 heat exchangers and supplied 20. All right, because we supply many heat exchangers, we can provide a higher efficiency, better designed heat exchangers at the same cost you're currently purchasing. The minimum you should do is have KLM review your designs. If your pictures look like that, you need to do something different. Okay. So we looked at safety, sustainability. The best thing to sustainability is reduce energy. We just talked about how to reduce energy in heat exchangers. We talked about how to reduce energy in distillation. Let's talk about pumps. And I'm actually out of time already, but let's talk about pumps for a second. Pump design and troubleshooting. Current pump designs have higher efficiencies due to safety models. If you're going to replace a pump, consider increasing the efficiency of the pump. Older pumps and motors might be 75% efficiencies. Newer pumps are greater than 90%. This is how the majors are getting 3% energy reduction. There will be a small cost impact, but it has a huge return on investment. Okay, so you look at the motors, you buy a high power factor on the motor, you go buy a high efficiency pump. Again, the minimum you should do, if you don't want to buy through KLM, the minimum you should do is have us review your specs. Okay. And there's simple things you can do in pump design. There's simple things you can do in the motors. You just specify them correctly. All right. Of course, we've probably done 20 pumps in the last 5 years. So we're buying 20 pumps. Your plant's probably buying 1 or 2 pumps a year. We probably can provide that pump cheaper than you can buy it. We have a senior team to help specify and supply your pumps. Because we buy many pumps, we can provide you a higher efficiency pumps at the same or lower cost than you're currently purchasing. So look at KLM for distillation equipment, for heat exchangers and pumps. And the minimum you should do is let us look at the specifications. So what have we talked about? Safety. Okay. We're a C student at best on safety, but we've come from an F. We've come from horrendously poor safety to average safety. We need to keep pushing in HAZOPs, in process studies, more ways to improve safety. Sustainability. The best thing for us to do in sustainability is use less energy. And we can use less energy in distillation. We can use less energy in heat exchange. We can use less energy in pump design. And so thank you for your time today. Thanks for attending. We've had over 100 people show up today, and I appreciate that. And let's look at some Q&As for a minute. Let's go back over. I think some of the Q&A questions we've already answered. So let's go back up and look. A tire bottom has a baffle and a hole in it. What is this used for? I mean, again, I mentioned you want the tower last traded dump on one side of the baffle. I want that baffle then to go through, I want that liquid then to go through the reboiler and then come back out. So I want all of the liquid to go through the reboiler at least once. It's got a hole in it, so when you drain the column, the level in the baffle will come out. This PDF, I can share this PDF. Typically, we're going to post it on Carl Clement's CPE YouTube channel. I've got a number of videos already posted there. You should go look at this. Function of the vortex breaker in the bottom. There's a swirl that happens as you're pumping. This vortex breaker stops the swirl, and you won't let gas go into your pump. A pump's not designed for gas. Most difficult process upsets you've encountered. Typically, they're power failures, and you need to improve your power failure reliability. If you get a high level and you're putting steam in the bottom of the column, you're going to probably take the trays out. The steam rumbling up through the column will take out all the trays. So power failures are particularly difficult. High levels are particularly, and levels are hard to level. We talked about this a little bit. Levels are hard to look at. And so power failures are difficult. High levels are difficult. And so you can look at this. Install an impingement baffle on the reboiler return. It is possible. I have a whole paper on what that baffle should look like. Send me an email and ask for the paper. I think it's actually published on, I can't remember, one of the major magazines published it early on. And of course, we're publishing a magazine for the last 7 years, Engineering Practice. I have a reboiler with capacity of 2 times 100%, one reboiler, isolated block valve closed without a PSV. BASM doesn't have to have a PSV. This is a great question because 3 people died at Williams ethylene plant because they blocked in a reboiler without a PSV. You need to have a study. You need to go look at that. Chemical Safety Board has a video about this. You need to go look at the video. You need to do a HAZOP, and you need to if you're going to block it in, all right, the code says any stamped vessel has an adjacent PSV. All right, so if the reboiler is a stamped vessel, which it is, law in the USA is that reboiler has to have a PSV. Now, what people do is they'll lock things open and they'll say, well, it doesn't require a PSV. That's not what the code says. The code says a stamped vessel will have an adjacent PSV. All right. And so, so they get around this by not putting any valves. If there's no valves, sometimes I'll let them take credit for the PSV on the tower. But you have valves here. And this exact same scenario that you had multiple deaths at Williams ethylene plant in Louisiana. So you need to go look at that closely. Desalter trip. I've got a whole series of videos on desalters. I probably need to do a webinar on desalters. Okay. And so typically you get high emulsions due to your pH, and the desalter will trip. So you need to keep your pH under control, and your and so a lot of people will put pH adjusters. A lot of people use there's a lot of people who use things I don't recommend. And so we could look at a desalter study for you, pretty easy. Galvanic corrosion in the columns. So galvanic corrosion is when I have mixed metallurgy. All right. So if I have a carbon steel wall, I probably need carbon steel packing. The vendor don't want to sell you carbon steel packing because they're difficult. If you're struggling to find carbon steel packing, come to KLM, we'll buy it. What I've done at 3 different ethylene plants And you got a recommendation of software programs for complex mass balances, highly integrated petrochemical plant. What I've typically done is I've taken 3 really sharp young engineers and I've trained them to build this complex mass balance. Okay. And so for an ethylene plant, I'll pull in a furnace model, I'll pull in utility models. And so all the major companies tend to build their own nowadays. The software companies have not done, they're very expensive and they're not as good as if you build it yourself. Okay. And so now it's going to, you can buy it for $1 million from one of these high software programs, but you can probably spend 200,000 on 3 really good young engineers and have a better program. Comparing stainless steel packing, carbon steel packing, KLM, I've done it 3 different times. KLM can help you train your young engineers how to do this. Comparing stainless steel packing, carbon steel wall, and carbon steel packing, what combination would last longer? Well, you got to think about galvanic corrosion. All right. So if you have water, if I have caustic, if I have caustic, I don't want to use stainless steel packing. I don't want to use a stainless steel wall. I don't want to use a stainless steel demister pad. But every caustic tower I go into has a stainless steel demister pad. So I want to use, I either want to use stainless steel and stainless steel packing, or I want to use carbon steel and carbon steel packing. That's what's going to last the longest. Okay. Certificate of attendance on the, I don't see any link for certificate of attendance on the chat box since it is disabled. Is the chat box disabled? If I click on the chat box, I can see this. So go up and click on your chat box. Certificate of attendance. If okay, make us. How is experience on use of mechanical vapor multiple stage for an inter-reduction, integration, and distillation columns? So basically, when you use, I call it a heat pump, mechanical vaporation recompression for energy reduction, it works. It works okay. You have another piece of equipment that you're running that you have to do maintenance on. All right. So what is typically used for is it makes the column smaller. All right. So, but I pick up an extra piece of equipment that I've got to do energy and I've got to do maintenance on. All right. Typically they're used for propylene columns. I've seen them used in propylene splitters a lot. You do. And I've got a paper that talks about this. It talks about high pressure propylene columns. It talks about lower pressure propylene columns, and it talks about this mechanical recompressor vapors. With the cost of maintenance nowadays, the cost of the compressors nowadays, you got to think long and hard. Is it the right answer? It's not just a straightforward question. The chat box is disabled. Okay, I'm probably going to go. Let me see what I can do here. Okay, the chat box is disabled. Copy. Can you see this link? All right. Copy this link right now. And can you see that link? What happened to it? All right. Type answer. Paste. Send. All right. So I'm trying to send it to you if I can. Okay. Mechanical recompression. Is exchanger having vapor lock in the shell side? Heat transfer rate will reduce. Okay. How do we know if it's vapor or fouling or tubes? So typically on the top of a heat exchanger, there should be what's called a non-condensable line where you remove the vapor out of the heat exchangers. If your heat exchanger doesn't have a non-condensable line, you need to add one. I'll try to include that in the next video presentation to talk about non-condensable lines. Okay, so you need to install a line on the top of the shell to reduce the vapors. All right, and that's called a non-condensable line. Send me an email and ask me that question. I'll try to answer it a little better. I'm unable to read the chat box. Type your answer, paste and send. How is a pump's motor current decided? Well, it's the current is decided by the horsepower of the, of course, I'm saying horsepower or kilowatts of the motor. All right. So how big a pump you need is based upon your requirements. Can you share the link of the YouTube channel you mentioned a while ago? All right. So let me share that link. Carl Comet's CPE. All right. Let me go find that. Okay. So the role of VFD in pump motors. Okay, that's a good question. Variable speed is a very good energy saving device. All right. So what we do now, we run a fixed speed and we put a control valve in front of it, and we put energy in with the pump and we take the energy out with the control valve. So that's really not very efficient. All right. So we can use a variable VFD drive in pump motors and only produce the amount of energy that is required. Again, there's a cost to this, okay? And it needs to be a medium to large size motor to make a difference. For a small motor, the variable speed controls is not worth it. You just do it with the control valve. If it's a medium to large motor, it makes sense to use a variable speed drives. Thank you. Thanks for your kind comments. Can the link be resent? My internet logged me out as you were about to share it. Sorry. Okay. Well, let me send this link again. All right. Chat box disabled. All right. So I'm trying to go through here. I'm sorry. I'll see what I'll see what the I'll try to figure out how to do the chat box better, because I thought the chat box. All right. Thanks for your time today. KLM would be happy to help you in a lot of these areas. We've talked safety. I didn't talk enough about safety. I need to talk more. Sustainability, I talked about quite a bit, about the best way from an engineering point of view is to use less energy. Distillation design, you can have a 10%, just replace your trays, which is low cost. You can do 10% less efficient, or you can do 10% more efficiency trays. Heat exchangers, I showed you some horrendous pictures. Pump design, if you buy low cost pumps and low cost motors, you're asking for your energy to trend up over time. Thanks for your time today. I think I've covered most all of the questions that we've got. So, all right. How to design a spiral heat exchangers. Is hot vapor bypass arrangement for condenser necessary for all cooling water exchangers? If I'm going to design it, I'm putting a hot vapor bypass. If I'm going to design it, I'm probably not using a hot vapor bypass. Okay. I don't really like hot vapor bypass. They're typically used for C4 systems only, but I'm not a fan of hot vapor bypass systems. How to design a spiral heat exchanger. Spiral heat exchangers are typically used for a heat exchanger that might sit on the top of a column. They're typically used for high fouling services where you have a lot of solids. So that's kind of what spiral heat exchangers are used for. You could find some really good articles. I got a friend that wrote some good articles on spiral heat exchangers. So you can find some good articles on that. So I've run over on my time. So thanks guys for your time today. hopefully we can help you some, and we'll try to do, I'll probably do a Rev 2, which talks a little less about distillation, a little more about heat exchangers, a little more about pump designs. So thanks for your time today, and send me an email, and you can go, and if it'll take me a couple of days, I'll have to edit this, and I'll have to post it on, so it'll be Carl Colmetz at cpe.com. All right. Thanks for your time.